This video is about weak acid-base titration, so something about it's going to be weak. You should already be able to identify weak acids and bases, calculate pH of their ion concentrations, and calculate the pH of a buffer system. By the end of this video, you will also be able to read and describe weak acid or weak base titration curves, calculate the pH during a weak acid or weak base titration, and identify and explain the significance of the half titration point. So the question of the video is, what is the concentration of ammonia in the Windex of 24.54 milliliters of 1.2 molar hydrochloric acid is needed to titrate 10 milliliters of the cleaner? So we're titrating a weak base and a strong acid. So think, how would a titration of a strong base and a strong acid differ from a weak acid and a weak base? How are they similar? So they're going to both have an endpoint. We need to know when they neutralize one another. So there will still be a need for some kind of indicator or pH probe that tells us when to stop titrating, right? So we still have all those words of standardization and neutralization, equivalence, and endpoint. But their endpoints might not be 7. So let's get to that. So here is a picture that shows our normal graph in red of a strong acid with a strong base where its equivalence point, or the steepest part of the graph, is at 7. If we compare that to the weak acid with a strong base still, the base is still strong. The titration curve starts a little bit higher because the weak acid has a slightly higher pH. It has a harder time, well, it increases drastically at first and then stops, right? It resists pH change because at this point we've created a buffer. We'll get back to that. And the equivalence point, which is between these two curves, or the steepest part of the graph, is much higher. Now the pH at equivalence is somewhere around 9. So what we're saying is, because you're adding a weak acid to a base, the weak acid in the base forms a salt which has the same common ion as the acid had. That creates a buffer that resists pH change. It resists pH change so well that the equivalence point will be higher due to the now basic salt you formed. Remember, we talked about how, yes, it will form a salt in water and there will be no acid or base left over at equivalence point, but that salt might not be neutral in this case. So it will be higher than 7 at equivalence, and the weak acid's titration curve starts with a higher pH with a slight bump. You can kind of see that. Again, the conjugate acid affects the pH at the beginning of the titration due to the formation of a buffer. Maybe we started with a weak base and a strong acid. So now you can see, again, the red represents what we used to have. A strong acid and strong base equivalence point was at 7. It looked pretty normal, nice and, equal. But if we're doing this with a weak base, notice it starts lower. It has a slight bump to it. When you're starting to add the acids to that weak base, you have a weak base and a salt that you're forming as they react. The salt you're forming has the same ion the base had. So that's why you're having this resisting of pH change. We colored it in purple to say that's where the buffer system would be. And its equivalence point's lower than 7, see? So you need to have a different indicator. It's still using an indicator, but a different indicator that indicates your new equivalence point that's lower than 7. So again, it starts lower, it should say, with the weak base and has a slight bump. One other thing we should look at is polyprotic acids, or acids that have multiple hydrogens. That means they're going to have multiple equivalence points. So they're going to start with low pHs, and as you add bases, they might buffer a little bit and hit an equivalence point pretty low. They might buffer a little bit again and hit another equivalence point because there's more than one H to come off. Remember, the first time the H comes off, that's the first equivalence point. The second time an H comes off, that's the second equivalence point. There might even be a third if you form PO3 minus 3. So I just wanted to make sure you point out you can see multiple S curves. When you're working with a weak acid or a weak base titration, the steps are kind of similar to we did with strong acid base titrations, but there is a small difference, and so you should rewrite the steps. Always write the reaction, but a double-headed arrow is used when they're weak. Start with an ice with initial value in moles. We did this before because we're not working with a Ka or Kb yet. We're just working with how much is reacting. Determine the changes in the mole ratios. The exit will be equal to the lowest initial value. Remember, we did that before, the limiter. And then determine the equilibrium values by subtraction and addition. If a strong acid or base is left over, you divide by the total volume and you negative log. And that's all the old rules. We're adding a rule to this. Number 7 says, if a weak acid or base is left over, calculate the pH using Ka value, and so icebox it, or Hasselbalch. And I'm going to be showing it with Hasselbalch because it's a little cleaner and easier to follow. So here's an example. Calculate the pH of 25 milliliters of 0.1 molar acetic acid. The Ka is given. if it's titrated with 10 milliliters of 0.1 molar sodium hydroxide. This is the exact same question I did when I did strong acid, strong base, except for I changed the acid to acetic acid or vinegar. So we're going to start exactly the same way we did in the previous video. We're going to write a reaction. Actually, it should have a double-headed arrow. We're going to write in our molarity. So I did that by multiplying the molarity times the volume here, and the molarity times the volume, and I put it there. Our change is going to be the lower of the two numbers, so I'm going to subtract by 0.001 and 0.001, add it to the other side. And at equilibrium, when we subtract, we get 0.015 acids, nothing in the base, a little bit of salt, which remember is basic, and water. Now what your options are is rewrite an icebox, but iceboxes need to be in molarities, and this icebox will be different because it will be the icebox with a salt in there. I really don't recommend doing that. Instead, because you have a weak acid and its conjugate, recognize that you have a buffer system, and that's why we'll be using Hasselbalch. So let me look at the icebox first. If you wanted to do an icebox type of example, here's the icebox we just did. The Ka is given. You would write your values in. 1.8 times 10 to the minus 5 is Ka. You say you have an unknown amount of hydrogen ions. You'd put your concentration of the salt in over the acid in so products or reactants. Remember, water is not included in the Ka, so we're plugging them in, find the H and negative log. But this is really confusing because it doesn't look like the Kas we've done before, right? It has initials for two things. So instead, if you want, you can just Hasselbalch it. So instead of doing all this work up here, I'm just going to do negative log of 1.8 times 10 to the minus 5, and the log of the salt, which is 0.001, over the acid, which is 0.0015. So I think this is a lot cleaner as long as you remember the salt is on top. So when I calculate it, boom, 4.57. I get the same answer if I want to do an icebox or if I want to do a Hasselbalch. The icebox will be confusing because a lot of people will do x squared over 0.015 or x squared over 0.001 and you'll get the wrong answer. So I think it's better to just associate weak acids with Hasselbalch. Let's look at after equivalence. So if you look at this one, this is the same question we did before in the previous video, except for I changed to vinegar again. So 25 milliliters of the acetic acid or vinegar, 35 milliliters of the base. We know we have more base left over, but let's just go through the motions. So here's our reaction. This is how much acid and base I have. When I subtract, remember I found that by multiplying. I take the smaller amount and I subtract it out and add it. At equivalence, I have a strong base left over, a basic salt, and water. What do you think will change the pH more? A strong base or a weak basic salt? I think the strong base. We're going to ignore that because it won't change that much. We're going to look at the strong base that's left over. If you have a strong base, you can just negative log the concentration and subtract from 14. So 14 minus the negative log of the moles divided by total volume. Remember that? 25 and 35. This is the exact same as a strong acid, strong base titration. And the reason for that is, remember when we looked at the curves just a moment ago? The curves ended at the same place. Right? So let me just point that out to you. Way long time ago in the same video, the curves ended at the same region. So we just calculated all the way up here. Right? So it's pretty important that you realize that if you have a weak acid left over, it's completely different than if you have a strong base left over. Right? The calculation is slightly different. Let's do this with weak stuff, bases instead. So this is strong acid with weak base. Right? So the acid is hydrochloric and the base is ammonia. So we're going to write them reaction together to form the salt and water. We'll write by multiplying the moles of each one. We'll subtract the lesser of the two values and find equilibrium. When we do that, we notice we have a strong acid left over, so we can just negative log the concentration. Negative log the moles divided by the total volume. So strong acids and strong bases just get negative log, just like we did in the previous unit. But in this example, we're going to still do strong acid, weak base. But I'm changing it so there's more base left over. So when we do our same exact setup, we put our moles in by multiplying, subtract the smaller amount, and write it out. I have a weak base left over. I don't want to just negative log a weak base. I can do another icebox if I'd like, and do a KB, which is why they gave it to us. Or I can Hasselbalch because I think it's cleaner. So, if you want to do the icebox, that's the icebox we just did, you have to plug the numbers into the KB, both the NH4 number and the base number has to go in. And this is why most students have a hard time because they don't know which one goes where. They wind up writing x squared somewhere and they get the wrong answer. What I would recommend doing instead was Hasselbalch using the basic Hasselbalch. So we'll put the negative log of the Kb that was given in the previous part of the question and the log of the salt over the base. And it makes it much easier. So it's a one-line calculation instead of a multi-line calculation where you have a lot of errors. Either way, you get the same answer, 8.86. It's basic because I thought I had a weak base left over. It's not extremely basic because it's not a strong base. There's not a lot left over, right? So it's kind of within the realm of possibility. Also remember, I have to subtract from 14. I probably didn't do that. It's shown that. One last thing about these titration curve is if you're working with weak acids and bases, there's something called a half titration point, and it's really important. The half titration point of a weak acid can be found by halving the volume of sodium hydroxide needed to obtain a neutralization. At this point, the amount of original acid equals the amount of conjugate base. So if you look at the equivalence point where the two curves were the steepest, that took us approximately, I don't know, let's say 26 milliliters. So half of that would be approximately 13 milliliters. Read back up. And that's where our half equivalence point is. Usually you use exactly half of the volume concentration. If that's true, whatever the molarity was, I use half of it and shift it to the right to have half of every substance. So I use half of the acid and it formed half the amount of ion I could have formed, and that too. In that case, if I wrote a Ka, it would all be half molarities, whatever that value is. If it was 2, they'd all be 1s, right? And that means the Ka, if I just cancel one on the top and one on the bottom, is equal to whatever the half molarity is. The Ka is equal to how many hydrogens you have, which means the power of Ka is equal to your power of H. What's our power of H at 13? I don't know, around 5? So our power of Ka is close to 5, which means our Ka is equal to 1 times 10 to the minus 5. You don't have to do all the work I was just showing you here. I was just trying to prove it for our math smart people. What I'm just trying to say is, I can figure out what acid is if I look at where its equivalence point is, half that volume, read back up, and say, hey, the pH is 5 there. At a half, that means the Ka is 1 times 10 to the minus 5. If I know the Ka of the acid, I can use a textbook or a Google search to figure out what acid it is. So just remember, at half titration, pH equals pKa. Because it's derived from Hasselbalch, the amount of salt was equal to acid. That cancel, the log of 1 is 0, so pH equals pKa. So the question of the video, I forgot to have these plugs in. Alright, fixed. What is the concentration of ammonia in Windex if 24.54 milliliters of this acid was needed to neutralize 10 milliliters of the cleaner? So we put 10 milliliters of this Windex into a small container. We put an acid that we knew about, we titrated it, and then when it came out, it was 24.54 milliliters used to make it equivalent, right? To change the phenolphthalein or whatever titrate indicator you used, right? So what we're going to do first is find what we do know. We do know we used 1.2 molar of the acid and 0.02454 liters, so we found the moles of the acid used, right? Next, if we know that's the moles of the acid, at equivalence, there's also the moles of the base, and we divide by how much base we have to get 2.94 molar. This is an actual old question. Remember, we should be able to find the molarity of any substance at equivalence just by doing an MAVA, if you want to think of it that way. This is a similar question we did in a previous video. But what I want to add on is, what is the pH if 12 milliliters of the Windex was used to clean a spill of 25 milliliters of the acid? So I had a 25 milliliter spill, which was slightly more than we use in the titration, and I put a little bit more cleaner on there, and that way I used to clean it up. I don't know about you, but I'm Greek, and in my family we use Windex to clean everything. So it's actually a pretty applicable question. So let's, now that we know a lot about them, find the moles of each. So to find the moles of the acid, we're going to do the volume, 0.025 liters, by the molarity of the acid to find the moles. We'll do the same for the Windex. So 0.0212 liters by the molarity we just found. And we found out how much ammonia, remember ammonia was the inactive ingredient in Windex. When we find the moles of each, we can subtract to find the moles that's left over. So this is a leftover ammonia and a salt. That means you can icebox this, but remember, if you icebox it, there's also salt left over, your icebox doesn't look normal, your Ka or Kb expression has 2 values in it, and it's very messy. Instead, what I was recommending you to do is, since you have a weak base left over, a weak base Hasselbalch's, right? So we just do POH equals the negative log of the Kb given, plus the log of the salt, which was whatever your limiter was, divided by the acid, or base, in this case a leftover. So it's your limiter divided by leftover. That gives me a POH, and that doesn't seem right because I was using a base, right? If you're using a base, remember you're finding a POH, so you have to subtract from 14. That means the pH will be 8.5. Maybe I use a little bit too much Windex, right? and maybe I should have actually cleaned this bill with water first. But in this case, we're seeing an applicable example. So you should be able to read and describe a weak acid or base titration curve, calculate the pH of a weak acid or base titration, and identify the significance of the hat titration point.